So section 5.3 is going to be a big one. This is where we're really going to jump into thermodynamics, starting with the first law of thermodynamics. We're going to define some values such as enthalpy, and we'll talk about how that's a state function. We'll learn to write and balance thermochemical equations and how to do enthalpy calculations using a few different techniques that we'll have. First off, we'll remember thermochemistry is a branch of chemical thermodynamics. It's the science that deals with the relationship between heat, work, and other forms of energy. We need to start to think about different substances as acting as reservoirs of energy. So they contain energy that can then, and we can add energy to those substances. We can remove it from them. And when we add energy to a substance, what's happening is we're increasing the kinetic energy of each of the atoms or molecules that make up that substance. So let's start off with defining internal energy. The total of all possible kinds of energy present in a substance is called the internal energy, and that is abbreviated with a capital U, very ambiguously. As sometimes you'll see a capital E, but in chemistry you're typically going to see a capital U. Now, we can add up all of the different kinds of energy within a substance and find out the exact internal energy of the substance. But typically, we're really not very concerned about that. What we want to know is how the internal energy of a substance is changing. And for that, we have this relationship between the change of the internal energy of a substance and the heat and work that are either added to it or removed from it. And this is what is called the first law of thermodynamics. So we have a sign convention that we need to follow. Energy can be transported into the system, resulting in an increase in internal energy. If this is true and the system absorbs heat, we're going to have a positive Q value. And if instead the surroundings do work on the system, then we get a positive work value. Energy can be also transferred out of the system. Okay, that system can release heat, or it can do work on the surroundings. Both of those values will be negative. We can see that here where we have our system in the center, and when the internal energy is negative, work and heat are being removed from the system. Whereas if the internal energy it's gaining internal energy, work is being done on the system, heat is going in. Now, I will mention that this is a little bit of an oversimplification. You could have a process whereby, say, heat goes in and work comes out, but if the work coming out is not as large as the heat going in, the system ultimately gains internal energy. Similarly, you could say have a system where work goes in and heat comes out, but there's more heat that comes out than work goes in, and then the system winds up losing energy. So you have to realize that all of these are possibilities. So the work that chemists are mostly concerned about is called expansion work, sometimes called pressure volume work. And this is basically where a system pushes back on the surroundings against a restraining pressure. This is happening all the time. Your body is pushing back on the pressure of the atmosphere, pushing in on it right now. And so there's this type of expansion work that keeps your body from just being crushed by the atmosphere around it. This is happening around us and to differing degrees in differing systems. So if we consider an example of this, we could have a system inside of the combustion engine. For instance, we could define the system to be the gasoline and the oxygen. And the surroundings is pretty much everything around that, including the engine. This reaction is exothermic. It's going to give off heat, so Q is negative. And the reaction pushes the pistons out, right, by expanding. So work is negative. And ultimately the gas and oxygen have decreased their internal energy by releasing it out into the world. So internal energy is an example of a state function or state variable. The value of a state function depends only on the state that the system is in and not how that state is reached. So we only have to have information about what we started with and what we ended with. It doesn't matter the path it took between the two. An example of this might be altitude or elevation. For instance, your potential energy difference will be the same going from the base of the mountain to the top, regardless of what path you took to get there. Okay, you're still going to have the same difference in potential energy, just so long as we know the end point and the beginning point. So chemists are mostly concerned about enthalpy, and we're going to talk a little bit about what that is. So enthalpy is defined as the sum of a system's internal energy and the mathematical product of its pressure and volume. Okay? The enthalpy is also a state function, and unlike internal energy, we cannot at all calculate the absolute enthalpy of a substance. But again, we're not very concerned about the enthalpy inside the substance. We're concerned about how the enthalpy changes during a chemical or physical process. So commonly chemical and physical processes occur at constant pressure. At constant pressure, we can make the substitution that P delta V, pressure times the change in volume, is equal to the negative work done by the system on the surroundings. And it's always going to be true that the arithmetic signs of delta V and W will always be opposite. So if you have a positive delta V, you're going to have a negative W. If you have a positive W, you're going to have a negative delta V. So that's important, because what we're going to do next is we're going to take this delta U and we're going to substitute in our original definition here of QP, heat at constant pressure, plus W. And then we're going to substitute in for P delta V this negative W. And what we're going to see is that work is going to cancel, and that the change in enthalpy is equal to the heat either added or released from the system at constant pressure. So we've already seen that we have good ways of measuring heat, and this is going to give us a good way of measuring this thermodynamic quantity, enthalpy. So why enthalpy particularly? So a lot of times chemists are going to just do stuff in the open air at their lab benches and stuff. This is under normal atmospheric conditions, and the external pressure is pretty constant. The pressure from room to room might vary a little, but not much, and not in any real significant way. So if only the work is done caused by expansion and contraction, then the heat flow and the enthalpy delta H for the process are equal, and this makes enthalpy a very convenient choice for determining heat and for measuring heat to determine enthalpy change. So, thermochemical equations. Basically, this is the same kind of equation that we've been using before, only now we're going to add the change in enthalpy during that process at the end. And we're going to write it kind of like this. So we're always going to write this out. And you'll notice a lot of the time that you don't always have those least common multiple coefficients here. Because you're gonna see is that this enthalpy is going to change when written like this, because it's an extensive property when written like this. Okay, if I say had two H2s plus O2 is going to yield two H2Os, well then this delta H value is going to double. All right, we will have situations later where we make this into an intensive property. And just like we did that with specific heat, what we're going to do is we're going to divide this by some quantity that makes it intensive. In this case, we're going to divide it by the number of moles that have either reacted or are produced. So you need to watch out for that later, and we'll show some examples of that. So if the direction of a chemical equation is reversed, the arithmetic sign of delta H is also reversed. So you can see that down here when we switch it so that we have our product starting and that goes to the initial reactants, we're switching the sign of delta H. Here is what I was talking about before. If the coefficients of the chemical equation are multiplied by some factor, the enthalpy change must also be multiplied by that same factor. So if we multiply everything by 2, we wind up multiplying the enthalpy by 2. If we multiply by a factor of 1/2, we multiply the enthalpy by a factor of 1/2. The change of enthalpy of a reaction depends on the physical state of the reactants and products. So typically we're going to show these. For instance, this would be different if we were producing, water vapor as a gas, or if we added liquid oxygen here. And you can see the difference between producing liquid water and producing water as a gas. Obviously, so some additional energy winds up being released when we go from gaseous H2O to liquid H2O, and you can see that results in a more negative enthalpy change. Let's look at an example here. A gummy bear contains 2.67 grams of sucrose. We have the formula for sucrose there. When the gummy bear reacts with 7.19 grams of potassium chlorate, 43.7 kilojoules of heat is produced. Write a thermochemical equation for the reaction of 1 mole of sucrose. So we're going to start by writing a balanced equation for this reaction. And it's a little bit of a tricky one, but I did it for you down here. We're going to start off with this guy. We're going to add 8 moles of our potassium chlorate. This is a combustion reaction, so we're going to wind up with CO2, water, and finally potassium chloride salt as the breakdown product of our oxidizing agent there, potassium chlorate. First, we'll determine the number of moles of the reactant. So we need to know how many moles of sucrose we had. We'll divide that by its molecular weight, which we saw how to calculate previously. And then we'll figure out the number of moles of potassium chlorate. and then we'll determine the ratio of one reactant to another here. We can see that we have 7.52 times the number of moles of potassium chlorate as we do sucrose, and that we actually needed 8 times the amount given our stoichiometry over here. So our limiting reactant in this case is going to be the potassium chlorate. Next, what we're going to need to do is to decide, so we take the limiting reactant, our potassium chlorate, and we're going to use that to determine our delta H change. And what we're going to do is come back here and look at the problem. We see that there's 43.7 kilojoules of heat is produced. So that's all of our heat right here. And we're going to divide that by the number of moles of potassium chlorate. And we'll see that for every mole that is reacted, we got 744 kilojoules of heat released. Now, because the equation as written represents the reaction of 8 moles, the enthalpy change is going to be a little different. Now we've figured out how many kilojoules of heat get released per mole of potassium chlorate. We need to multiply by the amount of potassium chlorate we'd like to react, and we can see as written that equation is going to produce 5,960 kilojoules of heat. So enthalpy changes are typically tabulated for reactions in which both the reactants and products are at the same conditions. This is called the standard state. So the standard state is a commonly accepted set of conditions used as a reference point for the determination of properties of, under other conditions. So what this basically allows us to do is that if we can just start to collect data about the enthalpy values of different things under a certain set of conditions, because if we tried to just collect data under all conditions, it would just be too much. And it's really ultimately kind of unnecessary, and we'll start to see why that's true. It is important to know what the standard state conditions are. So under the IUPAC standard, the standard state conditions are 1 bar of pressure, and solutions will be at 1 molar concentrations. So when we're talking about the enthalpy change at the standard state, you're going to see a superscripted O in the enthalpy change. Like you see down here, this little guy right there. The usual temperature that we're going to be talking about is going to be 298.15 Kelvin, or 25 degrees Celsius. And so we got 1 bar, 1 molar solutions, 298.15 Kelvin. So the enthalpy changes for many types of chemicals and physical processes are available in the reference literature. That's where we've started to figure out what the different values are at this standard state. We're going to recall that delta H is an extensive property, and that means that it's proportional to the amount of substances involved. So what we're going to do is what I was discussing earlier. We're going to make it an intensive property by normalizing it to a per mole basis. We're going to take the typical delta H and we're going to divide it per mole. So the standard enthalpy of combustion, for instance, is the enthalpy change when exactly 1 mole of a substance burns, combines vigorously with oxygen, under standard state conditions. So even though when you burn something, it's going to produce different amounts of moles of CO2 and water and possibly some salts or something like that. We're going to normalize it to the number of moles of a particular substance that we started off as our reactant with oxygen. All right, let's look at an example of that. The enthalpy of combustion of ethanol is negative 1,366.8 kilojoules per mole. This is the amount of heat produced when 1 mole of ethanol undergoes complete combustion at 25 degrees Celsius and 1 atmosphere of pressure, yielding products also at 25 degrees Celsius and 1 atmosphere of pressure. And we can see an example of how we would write that down here. We're going to have our ethanol. It's in a liquid state because that's the standard state of ethanol at 25 degrees and 1 atmosphere, plus the stoichiometric amount of O2, whatever that might be for the initial reactant. In this case, it's 3 O2s. We're going to produce CO2 and water exclusively because we only started off with a carbon, hydrogen, oxygen compound. And that's going to release enthalpy under standard conditions. So we write the little circle right there of negative 1,366.8 kilojoules. So we have tables and tables with tons of these values. You take any substance, you can see what the combustion reaction would be for it, and you can see what the enthalpy of that combustion at standard state would be. There's a more complete table at the end of the text that you will need for some of the problems. So, as that previous figure suggests, the combustion of gasoline is a highly exothermic process. We want to determine the approximate amount of heat produced by burning 1 liter of gasoline. We're assuming that the enthalpy of combustion of gasoline is the same as that as isooctane. Where that assumption's coming in is that gasoline is actually a mixture, so this is kind of a more complicated problem than this, but a large amount of it is isooctane. And we're going to need to know the density of isooctane, and that is 0.692 grams per milliliter. So let's take a look at this. So if we had a liter of isooctane, one of the first things we're going to need to know is how many moles that is. So we start off with that liter. We convert it into milliliters. So 1 liter is 1,000 milliliters, right? Now we need to go through the density to figure out how much mass that is. So we'll times it by 0.692 grams per milliliter. So we would know if we did this calculation right here that there's 692 grams of that isooctane in 1 liter. Then we need to figure out how many moles we have. So we would have had to calculate the molar mass of the isooctane to get the moles. And then finally we look up this value that we can see in table 5.2 that says that for every mole of isooctane burned, we're going to get negative 5,460 kilojoules. We'll multiply by that, canceling our moles, and we see that that 1 liter produced negative, well, what would that be? 33,100 kilojoules. Quite a bit of energy. So one thing that can be kind of interesting is the idea of renewable fuels from algae. This is a little vignette that was in the book that I thought was quite interesting. Instead of burning fossil fuels, one thing that they can do now is actually genetically modify the algae, grow it in these large troughs, harvest it, then they centrifuge it to extract it out, and then they're able to process out high-grade fuels from it. Quite interesting stuff when you're thinking about all the carbon that we're releasing on the atmosphere to produce climate change. This actually starts off the life cycle of our fuel as taking the carbon out of the atmosphere. A very natural process. So another form of standard enthalpy is called the standard enthalpy of formation. This is the enthalpy change for a reaction in which exactly 1 mole of a pure substance is formed from its constituent free elements in their most stable states. A lot of assumptions underneath there. Under state conditions, standard state conditions. All right. So, for example, if we have CO2, we're going to start off with carbon in a solid state because that's the stable state of carbon at standard conditions. O2 would be a gas. We're going to combine those together to produce CO2 as a gas because, again, that's the state we would typically see it in. And we're going to get that the enthalpy of formation of this reaction, which is the same as the standard enthalpy for the reaction is written, is going to equal negative 393.5 kilojoules. This is essentially a combustion reaction, so it's not surprising that this is exothermic, but a lot of times you're going to see that the standard enthalpy of formation is really going to be an endothermic process. You have to put energy in order to produce something from its elements. So an important thing to note here is that the standard enthalpy of formation of an element in its most stable form is equal to 0 under standard conditions. So to produce CS, for instance, that's 0. O2 gas, that's going to be 0. So sometimes you can, kind of skip looking it up in the table if you're sure that that's going to be a 0. All right, so let's look at some examples here. We're going to write the heat of formation reaction equations for, we have ethanol there as a liquid, and then we have calcium phosphate as a solid. We're going to remember that the change of enthalpy of formation reaction equations are for forming 1 mole of the compound from its constituent elements under standard conditions. So, to produce ethanol, we're going to need 2 moles of that solid carbon in the form of graphite, for instance. It's one of the allotropies of carbon, plus 3 molecules of hydrogen gas, plus a half of a molecule of oxygen gas in order to have the stoichiometry correct and have a 1 in front of here. That's what's important. You could have balanced this in any old way that you would have liked, and then just divided each of the coefficients by whatever you had in front of ethanol here, but you want your product to have a 1 in front of it here to be when you're calculating the enthalpies of formation. For calcium, we have a similar process to produce the calcium phosphate, and again, we're getting that 1 in front of the calcium phosphate. There are 2 ways to determine the amount of heat involved in a chemical change. We can measure it experimentally. We saw how to do that with calorimetry. Or we can calculate it from other experimentally determined enthalpy changes. Some reactions can be very difficult, if not impossible, to measure directly. But what we can do is we can just have like kind of a bank of very simple reactions, and then we can use this technique called Hess's law in order to use those simpler reactions to figure out the more complicated reactions. So Hess's law states that if a process can be written as the sum of several stepwise processes, the enthalpy change of the total process equals the sum of the enthalpy changes of the various steps. And this is kind of an extension of the idea of the state function. It doesn't matter what processes we put together so long as we start with the thing that we have and we finish up with what we want. So let's take a look at an example here. We can think of the reaction of carbon with oxygen to form carbon dioxide as occurring either directly or by a two-step process. So the direct process would be carbon solid plus O2 gas equals CO2 gas. We've already seen that. In the two-step process, first carbon monoxide is formed, and carbon monoxide reacts further to form carbon dioxide. So in this scenario, we're going to first add one oxygen to our carbon to make carbon monoxide, and in the following step, we're going to take that carbon monoxide, add the other oxygen, and form CO2. And if we knew the standard enthalpy changes for both of those reactions, what we can see is that when we sum these two together, we'll get this down here, and when we cancel the COs, our spectator species, just like we did when we were doing redox reactions, we'll get our original equation, and if we sum these two together, we'll see that that equals the delta standard enthalpy change that we already knew CO2 to have. Here's a diagram of this. So basically what we were saying is that carbon plus oxygen going down to CO2 is going to have the same enthalpy change as going from carbon to oxygen, and then carbon monoxide to CO2. So we can also use Hess's law to determine the enthalpy change of any reaction if the corresponding enthalpies of formation of the reactants and products are available. The stepwise reactions we consider are decompositions of the reactants into their component elements, for which the enthalpy changes are proportional to the negative of the enthalpies of formation of the reactions, followed by recombinations of the elements to give the products with the enthalpy changes proportional to enthalpies of formation of the products. So that is a big statement there. Let's take a look at the math, because I think it's actually a little bit easier. So basically what we're going to do here is we're going to look up in the table all of the standard changes of enthalpy of formation for our products. We're going to multiply each one of those by the stoichiometric coefficients. That's what this n is here. You know, if you're looking at the equation, what are the coefficients in front of that product? Okay. And then we're going to go ahead and we're going to sum all of those together. That's going to be one value. We're going to do the exact same thing for the reactants. We're going to sum them all together. That's going to be another value. Then we're going to take the product value that we got, and we're going to subtract out the reactants value that we got. Let's take a look at an example. What is the standard enthalpy change for the reaction when we have 3 nitrous oxides plus water as a liquid? That's going to go to 2 nitric acids plus an NO gas. What is that going to be? So if we went to the table, okay, what we would see is that so we've got to start with our products, right? So we're starting on the right-hand side of this equation. If we looked up nitric acid, we would see that it has a standard enthalpy of negative 207.4 kilojoules per mole. We multiply that by the coefficient of the nitric acid, that number of moles, and that's going to be one of our quantities. It's 1N delta H, okay? Then we do the exact same thing for NO. We look up its value, we multiply it by its coefficient, we add these two together. That is this whole big piece right here, all right, including the sum. And then we do that exact same thing for the products. And we take this whole first value as represented by this whole top row right here. We subtract out this whole second value here. And we get the actual standard enthalpy change for that reaction. That is everything that I have for this presentation. I have a lot of good examples in the homework of these problems, and I would encourage you guys to take a look at them.